Welcome everyone for today's ISyE seminar after a while, I guess. So we are very excited to have Dr. Nicolas Stier-Moses. He's the director of core data science team of Meta, as you may know, formerly Facebook. Prior to joining Meta, he was an associate professor at the Decision Risk and Operations Division of Columbia Business School. And also at the Business School of Universidad Torquato di Tella. And he received his PhD degree from the Operations Research Center of the MIT. As the director of the core data science team, his work draws inspiration from a rich and diverse set of disciplines, including operations, statistics, economics, mechanism design, machine learning, and computational social science. And so we are very excited that he has agreed to give a talk in our seminar, and today is going to tell us about Bernoulli congestion games and convergence. So Nico, whenever you're ready.
Cool. All right. Good afternoon, everybody. I'm really happy to be here, and I'm only sad I couldn't go in person. That would have been fantastic. But well, let's continue with the Zoom meeting for this time. So yes, so I'm going to be presenting a talk about congestion games, and I've been interested for a long time in the mix between congestion, risk aversion, and the way that people perceive utility, and stochastic. And this is an instantiation of this in which we study like some form of stochastics in these games and look at limits when the number of players grow, which is like a topic of great interest, I guess, to give some emergence to wardrobe games and games of that type that we have been studying for really a long time. I wasn't planning in the talk itself to speak a lot about Meta and what my team does in the company, but we can defer that to the questions or to an informal meeting after the talk. If people are interested, I'm happy to talk more to you about that and opportunities to collaborate or opportunities to do things together. Fantastic. So coming to slides then. Congestion games, like really, as we have studied, are really interesting because it allows us to abstract away many of the real world complications and look at interrelated decisions in which the interrelations are expressed through the congestion of resources. And in this particular case, so what I want to focus on is in a network game where people have to decide what route to take from origin to destination, and people interact through the externalities they generate on the different roads or edges that they select in the network. And the particular thing I want to focus on for this talk is on what happens when you have a very large population of individuals. So in the setting of atomic games, you have different players that will be making decisions. And some of these players may or may not show up on that day when you're trying to travel. So as people who have experienced traveling, so at the same time, we know that we can expect a given traffic or a given number of players that will materialize on a given day. And the question is how we can make use of that information to make actual trip decisions. You know, besides my, I guess, earlier interest on congestion games, actually it's funny that the story of why I'm working on this topic with this particular set of co-authors that I should acknowledge, and I haven't, so let me go back because I haven't done that explicitly. I want to. So this is joint work with Roberto Cominetti, Marco Scarsini, and Mark Schroeder. So the four of us met in one workshop in Germany many years ago in which I was talking about budget and auctions in the context of Meta. And in that context, what we were doing is we were trying to randomize the participation in the auctions by the players. And in that randomization, at the end of the day, in the auction, not everybody would participate in all the auctions. And there was this coin flip that will make the determination of what player participates in what auction. So in that context, and given our interest, like Roberto, Marco, Mark, and me on these congestion games, we started thinking about like these coin flips to model the participation in congestion games, which led to the papers I'm going to be speaking about today. So to think about this, so the usual setting that if you go back to Wardrop in the 50s, when they look at this continuum of players making shortest path decisions in networks, was that at the end of the day, when you have too many players, too many cars, the decisions are fluid, and like every single car is really small compared to the demand in the network, and therefore we can think of cars as something fluid and continuous. Now, the question is why, what validation do we have that in an actual transportation network, things are indeed continuous and the Waddrop model applies? And there were many papers in the past, like the most famous by Horry and Marcotte in the 80s, that proved that if you take a splittable atomic congestion game, and then you let the weights of the players go to 0 and the number of players go to infinity, then the equilibrium of this game converges to a Waddrop game, which is great. It's a great start, but doesn't describe all the different possibilities about the actual networks that materialize in practice. So we start from there and we look at the atomic congestion game that is unsplittable, and we look at these limits, and we looked at understanding the equilibria of these atomic games with the perspective of efficiency. And several of us work on price of anarchy type of results in the past. So we want to understand what's the combination of the interrelation between the inefficiency generated by these in these networks and the stochastics, in this case, the stochastic demand that we may see in the network. So that's the plan of what I intend to discuss today. This took the form of 2 different papers. The links to the papers are in the last slide, and I can give a copy of this PDF to you after the fact, and you can post it in your list or wherever you have your talks. So that way it's easy to get there. So the talk will have 2 parts. I'll talk a little about the inefficiency of equilibrium, define the game, and then I'll go back to convergence and talk a little about that. That's the plan for today. This picture, it's a normal scatter plot between time of a day and transportation time for a road or for travel. The only reason I put it here, although I'm not going to be considering any dynamics in this talk, like things are going to be totally static in terms of the game. What I want to illustrate by this picture is that at equilibrium, when you look at different days, every dot here is a different day. When you look at different days, you see that what emerges is not a convergence to a given travel time, but what you see is that at equilibrium on different days, you may have a distribution of travel times. And that's kind of my point today, is that an equilibrium itself can be a stochastic object that may depend on different realizations that may materialize day after day. And I want to explore together what are the consequences of looking at equilibria as the solution of a stochastic game, and whether at the equilibrium itself, like the equilibrium is going to be a realization of something stochastic, and what happens there. So that's kind of a motivation for this in terms of what we see in the real world. Okay, so let me start by talking about the Bernoulli Games, which are motivated by what we discussed earlier. So there are many players in a game. Let's think of cars that want to go from their origin to their destination, for example, from home to work every day. So we have a large but finite set of players. Then these players are going to select resources. Let's think of the resources to be the arcs or the roads in the network. And the strategy of the players is going to be a subset of the resources. And we can think of that as a path from origin to destination. Typically done in these games, we have some congestion function. We usually call that a cost function that maps how many players select a resource to how much it costs for that resource. So how much cost is realized in that resource. And we can think of that as a congestion in that arc, which has to do with the congestion that is perceived coming from the load that comes from how many people selected that arc at equilibrium. So small example, just to set ideas. This is called the Pico Network. And it's like the simplest example you can think about, because there are 2 nodes and 2 arcs. The cost function is given by, in this case, the upper arc has a cost of X, which says that every car that selects that arc takes an amount of time equal to how many cars selected that arc. And then you have the bottom arc in this example that has a constant travel time of 2. So in that case, it's independent of how many cars selected that arc. And this is finite game, so you can write this as a 2x2 game in this case, because there are 2 players and the 2 players have 2 options. And what you see in that matrix on the right of the slide is actually the payoffs or the cost fund, the realized cost depending on the strategies of the players. So if the two players select the upper path, the two of them, so there are two cars in the upper path, and therefore the two of them will experience the cost of 2. If one selects the upper path and the other lower path, the one that selects the upper path has a cost of 1 because a single car went there, and the one selects the lower path has a cost of 2. And if the two of them select the lower path, because the constant also both cars get the cost of 2. So that's the simplest setting of an atomic game in this case, and this was what was studied by Rosenthal in the 70s and proved that this game, this atomic game, is potential and gave a way to compute these equilibria in games like that. So that's kind of well known. What we want to add to this game is the last bullet, where the last bullet here is that now, out of all these many players that are there, some of them may or may not show up in the game. So let's add to the definition of this game a random variable yi, which is the realization of whether the person showed up or not on this particular instance of the game. And let's call pi to be the probability of that happening. All right, so in this case, what we have is a game with a large population, but now the actual game may be played by a subset of all these players that may be there or not on a given day. If the player is not there that day, what happens is that the player incurs no cost. So if you look at the expectation, notice that PI is not a decision, this is just a realization. So maybe that person intends to go to work, but at the end of the day, the person is sick and cannot make it and will not go to work, or something else happened, which is not allowing the person to go to the office, maybe working from home and connecting to the meetings by Zoom. So that trip never happened. So in terms of the expectation of the cost for the player, so we multiply the cost condition of the player traveling by PI, which is probably the person actually does the trip. Okay, so that's the setting, and this is the initial game that we want to analyze and explore.
Sorry, Nico, I want to make sure I understand.
Yeah.
So the cost function, should I think of the argument to the cost function as the expected traffic, or should I think of it as the realized number of people who choose that route?
The latter. It is the latter, and then you can take expectations. But the actual cost function takes as an argument how many people actually showed up in that place.
Okay, so if I had like 5 people, they all choose their route, then we flip coins to decide who actually is going to show up. And then the cost I incur is based on the realized congestion on the routes I chose, assuming that I'm one of the people who showed up.
That is totally correct, yes. And then we have 2 sources of stochasticity here. One is the one I'm talking about, the person may or may not show up, and the other is mixed equilibria. So because it's an atomic game, you may have mixed equilibria, people may be randomizing across different paths, and then different people may end up realizing different paths, and that's going to be part of the expectation that we may take on the cost function as you asked a second ago. So
but importantly, when I'm making my routing decisions, I don't observe who shows up. That's just made in advance.
That's the key point here, that you're making the routing decision ex ante and before knowing the realization of all this. And depending on the assumption, we'll talk a little more about that. So I think that's the important point here. But yes, okay. So we assume this is a static game. So we don't assume that, I mean, in practice, it may be that also you take the first arc of your path, and this is going to be correlated to how many people actually showed up that day. And if you can then maybe switch decisions, at that point, you have much more information. So we are not thinking about that because we're static games. We're not thinking about revising the strategy as soon as you get more signal from the initial part of the path that you're taking. Although, I mean, that's a totally valid follow-up type of discussion that we may have.
And the participations are all independent across.
Sorry, Chris.
The participations are all independent across players.
Indeed. So we are assuming that. I don't think in practice that is the case, because things are going to be correlated. For example, if the reason people don't travel is because of weather, then on days there is bad weather, it's more likely that more people will not show up to work. And so there is some correlation devices here that will induce some coordination on the decisions. But indeed, for the assumption of the particular paper, we assume that all the PIs are stochastically independent, And basically, I'll talk about this in a second. If all the P's are the same, or all the PIs are the same P, at the end of the day, the number of people that will show up on a given day is going to be binomial with the population of N, which is how many players there are, so that's the demand, and P, which is going to be the probability that a person shows up. And I'm going to try to justify why looking at these binomials makes sense, but then we'll have a device to analyze this, which is going to be through the binomial distribution. And then in the limit, the binomial will go to a Poisson, and that Poisson is what will allow us to analyze some of these in the limit when P goes to 0. So that's, I'm kind of anticipating forward what was going to come later, but so you know where I'm going with this. Okay. Questions? Yes.
Yes, Nico. So you're defining CE over the real instead of integer because you are, for this model right now, you don't need it to be defined for real, but going forward you need it, right?
We'll have weights later, so which is why I have reals. But yeah, totally. For now, this is all only the integers, and there is no reals yet. Yes, you're right. You're totally right. Thanks for noting that. But yeah, totally fine. Thanks for all the comments and questions. I'm really happy to continue with this. I like interactive seminars more than like me speaking all the time. So that's fantastic. So now let's look at the stochastic game. Now, still 2 players, people will show up with probability P1, P2, but let's look at the perspective of a given player. So if I'm player number 1, I know I'm going to be there because I'm making the decision to travel. So conditional on me traveling, what I'll see is I'll see 1 coming from me, plus I'll see from the other in expectation a P1 contribution to the cost function. And that's based on the question before. I'm taking the expectation after I evaluate the cost function. So this is not C of expected value of the load. This is expected value of C of the load that gets realized on that day. In this case, the cost function is X. So, then the expectation commutes, but that's just a detail because of this particular instance that we are playing with. Okay, so the payoffs for this game is going to be 1 plus P2 for player 1 if both of them play up, 1 plus P1 for the second player when both of them play up. In the other cases, there are constants because it's a single player selecting one arc, the only arc that has a dependence on the load, and therefore there is no probabilities in any one of the other 3 entries you see in that matrix there. Okay, all okay with the game? So with the basics of the assumptions we are taking for the game? Fantastic. So in this case, then we are defining a Bayesian Nash equilibrium because there is some stochastics here. As I said, the source of stochasticness comes from both the mixed strategies and from the realizations of who shows up in the game. And yeah, I'm trying not to use a lot of notation for the talk, but this is some notation that may be helpful in some of the subsequent slides. So we have yi is a random variable that says whether the player I is playing that particular day, and xye is whether player I selected the edge E in that strategy S. So that's why it's the mix between the random variable yi and the indicator whether the edge is part of the strategy. And then xe of S is counting how many people show up for an edge E under that strategy. So it's just summing the random variables. All this is stochastic and depends on both, as I said, whoever shows up in the game, which is coming from the participation probabilities, and if we are considering mixed strategies, on the mixed strategies. If you consider pure strategies, then the rest is deterministic here. Okay, so what is an equilibrium here? What's the base Nash? Well, conditional on me being traveling, I'm there for sure in the edges I selected to travel. The rest is going to be Bernoulli. So the rest of the players may or may not show up. Bernoulli, if we look one by one, it may be binomial if we assume that all the probabilities are the same. So this is basically writing that in symbols, saying that conditional on me being there in the arc, the equilibrium is one in which I minimize the expected cost. And this is the question earlier. As you can see, the expectation is outside, and you evaluate the C with the realization of the random variable. And what I'm saying is that I select the strategy that minimizes that expectation versus any other strategy I may select. And look at this, we discussed with some of you before about this is looking at expectations. So this doesn't add any risk aversion or anything else to the way people make decisions here. Okay. What I want to do, I want to look at relatively simple model because I want to look at the price of anarchy. and I want to have a handle on characterizing equilibria, so then I can prove something about the efficiency of that equilibrium. Okay, so that's why I'm doing this. I think it's an interesting open question about what happens when you add risk aversion or other factors to this simple game. So the game is simple, the analysis will not be as simple. I'll talk a little about that. So first thing to note, and this is not a surprise, like maybe doing the same thing as Rosenthal does from the paper in the 70s, in which you formulate a potential function and then you prove that the minimizer of that function is an equilibrium. You can do the same. Only difference here is that the sum here, you see that the second sum, which goes from k equal 1 to big N of E of S, that's random, but still everything goes through and you can prove that the minimizer of that is an equilibrium, and therefore you can minimize it and find the equilibrium again. So what that says then is that this Bernoulli congestion game supports an equilibrium in pure strategies when all the weights are 1 when you start from the basic game, which is a good news because then you can analyze that equilibrium. An important thing when you look at price of hierarchy is to compare solutions based on the same yardstick. And the yardstick here is going to be the total expected cost. So if you are the social planner here, now you know that on different days you have different realizations of the players of the actual game. And then after that, you can maybe select how people are going to travel. And depending how people travel, what happens is a different outcome about the total transportation time in this network. So when you write all that, what you're basically computing is the expected total cost. And the expected total cost you can compute as for every arc. You can look at how many people showed up in that arc and what's the cost of that, how many people showed up in that arc. So that's what was being displayed there. So you as a central planner, so now you can make different assumptions. You as a central planner, do you have access to the realization of the player participation, or you do not have access to the player participation realizations? So if you don't have access to that as a social planner, what you can do is you can still tell people what path to take to go to their destination, but it may be that after you told the person what path to take, they decide that they decide, or maybe they are randomly assigning to the population that do not travel, and then they are not present in the network. And whoever gets to travel then needs to select the path that is assigned by the central planner, and then the cost is going to become realized that way. So that's what we assume for this paper. So we call this I guess a non-profit central planner. So again, a non-profit central planner is a planner that doesn't have access to the participation realizations at the time they do the routing decision. If as a central planner, like you're a profit, meaning that you know the realization, then it's a deterministic game, because first you wait for the realization, then you know the actual demand, you can route everybody optimally, and that's it. I mean, then everybody takes the optimal path, and you're doing the minimum possible cost for that realization, and then you can take the expectation for the cost here according to what's the probability that you have so many players in that game that day, right? So, but that's a very powerful central planner because they have access to the realizations. Because we want to look at the inefficiency of equilibria, we don't want to give the central planner that much more power than the players. So we consider that both the central planner and the players do not have access to the realization of the participation. Let me stop for a second because there may be some details there. I want to make sure everybody got that. Okay, so that's
so basically the price of anarchy here is because of the inefficiency of selfish strategic behavior, but not because of the uncertainty about realization, because that happens both for the actual game and the planner's problem.
Correct. But I want to look at that inefficiency as a function of the uncertainty. So if you consider the uncertainty being whatever, maybe designed by an adversary, then the worst possible gap or the worst possible price of hierarchy is going to be when p is equal to 1, when everybody is present with probability 1, because in that case, we know that the worst possible model is the atomic game in which we know the price of hierarchy is equal to 5/2. The way I want to refine this, I want to make this a function of that p and see how that price of hierarchy changes when p is equal to 1 or when p is very close to 0. And that's going to be the center of the talk, at least on this first part of the talk. But great question. So that's exactly the point.
So a quick question. So, I mean, I understand the difference between the profit and the non-profit central, like social planner, but do we know how bad that gap can be? Like, is there
that's a type of price of information type of bound, which is what we're working on right now as a follow-up to this paper. So here, because the focus was price of hierarchy, we look at the non-profit social optimum. I think the next relevant question is how the non-profit social optimum compares to the profit social optimum. And that's a very interesting and important question, which is what we're working on currently with the same co-authors.
Oh, okay.
Because I think it's a really cool question about what's the value of that information of knowing these probabilities. Yes, exactly. All right, price of hierarchy, price of stability is the comparison of the best and worst equilibrium in the setting we have looked at for any arbitrary network. So the worst case network for this. I'll skip this. I assume that most people know this. If there are questions, happy to go deeper into these definitions. And quick, brief summary of related literature. Many people have worked on related things for a long, long time, starting from Wadrop and many other people in the 50s and 60s. Then we have the potential games of Rosenthal in the 70s. A lot of activity on price of hierarchy for congestion games in the last 2 decades. So super interesting work. I think related to this, many people have looked at stochastics, both from the demand and supply sides in the same type of setting. And many people have looked also at other games that relate to what we're studying and derive bounds that are compatible with what we're studying, although maybe their motivation was different. And let me mention maybe a few things here. So Clear and Schaffer have a really nice paper. They look at the perception of cost by players. But when you look at the math, at the end of the day, looking at this term of the perception of players, you can reposition that perception into a way that fits these stochastic type of elements that we are exploring here. So whatever bounds they give, you can transfer into our model, and that will give bound for us. So some of the bounds that we end up making here were known from those papers that study a completely different object, but the things go one-to-one. So that was very interesting. In a way also, although some of these bounds maybe transferred some bounds for us, by this analysis, which is more explicitly on this topic, we can, I guess, complete the result and provide a full curve for the piece between 0 and 1, as I described earlier. Anyway, so this very interesting, very active literature on this, which is really cool. I'm really passionate about this. So let me define for a second the price of hierarchy as a function of P. And the definition of price of hierarchy as a function of P is one in which all the players have participation probability equal to that P. So in that way, we can simplify the game, and that leads to a nicer analysis, because if all the PIs are P, then the participation is Bernoulli, and then we can explore things from the Bernoulli optics, which will allow us to compute many things that we wouldn't be able to compute if we just have, sorry, when I said Bernoulli, I meant binomial. Sorry, I mixed up. So if all the PIs are P, then we can explore the whole thing from a binomial optics, which is much easier than summing many Bernoullis with different parameters, which will be harder to analyze. So the good thing here is that although we start from a game in which all the PIs can be arbitrary, we have this result that things are monotone, and the price of hierarchy for any arbitrary game with all the PIs being whatever we want can be bounded above by the price of hierarchy when you take the maximum of the PIs. So give me any game where all the PIs are whatever. Let me take the maximum PI out of all the PIs you've given me. I can tell you the price of hierarchy is going to be upper bounded by that. So that says then the price of hierarchy of P now constant is monotone, so it's non-decreasing because of that result. And then that says I can plot the curve of price of hierarchy as a function of P, going from 0 to 1, and see how that grows over the different P's from 0 to 1. What I know in advance is that when P is equal to 1, that's going to be 5/2. That's a well-known result from like last decade. And we have the matching lower bound, etc. We know everything about that. What I want to know is what happens on the other extreme. When P goes to 0 and you take the limit, when N, the number of players, goes to infinity, P goes to 0, you would expect, because of all the stories we discussed earlier about Wardrop and the non-atomic games, that the whole thing goes to 4/3, which is the bound for the non-atomic games. That is also well known from 2000s or so. And I want to see whether that continuum happens, how, and that's what we get to do here. Okay, so additional assumptions. One is that I'm going to assume that the players are the same, so the PIs are P. I described that. That's without loss of generality for the reason I said earlier. The very strong assumption I'm going to make is that the cost functions are affine, and that's not without loss. Things are very different when you take different cost functions. The reason I want to do that is because I'm going to take expectations on the cost functions. If you have higher order polynomials for the cost functions, then I need to work on this game for the binomials, for the higher moments of the binomial, and then things get really messy for me to work out the formulas for the price of anarchy. So that's a very strong assumption, and it's a nice open question about what happens when you take higher order polynomials for the cost functions here. Okay, so what's good about the binomial model is that now if you assume that all the PIs are P, then my adversaries in this game are going to be many people that are going to be all the same that may show up with probability P. So when I look at the realization of the load in a given arc, this still is a congestion game because it depends on how many other players are there. So if you look at this game of X and 2 as the cost function for the arcs, I can translate this atomic Bernoulli game into a normal atomic game, in which the cost functions I can replace by the expectation of the binomials. And the expectations of the binomials are the following. If I'm going to be there, my contribution is going to be 1. For whoever else is going to be there, the contribution is going to be X minus 1, which is the rest of the other people that are going to be there. Each of them is going to be there with probability P. So that's what you see, 1 plus P times X minus 1. So we managed to transform, and that's because I'm taking expectations. Some people look at the first moments here. I can take any of these Bernoulli congestion games. I go through this to the step in which we make this homogeneous and all the PIs being P because of the monotonicity result I told you earlier. And now I can switch into a standard deterministic atomic congestion game that I can study and explore using the tools that we know from before. And using that, now I want to explore the price of anarchy in this game. So this is just a reminder for those of you who have worked in this space. You may have seen the lambda mu smoothness results, which is basically a property for the game and the cost functions, that if you have that, it translates immediately into a bound for the price of anarchy. So this has been explored by many people. Ralph Garland has a nice paper summarizing the whole technique. Many people use that even before the paper of Tim Ralph Garland, in which we look at lambda and mu, and playing with those two parameters, we can then define the price of anarchy for the game. So that's only the starting point of my study. So I'm going to look at for what lambda mu my game is lambda smooth, and then use this inequality in the lemma to have a bound for the price of anarchy, which is well known. Okay.
Hey, Nicholas, can I ask a question on the previous slide?
Of course.
So why do we need homogeneity here? If we're assuming affine functions, can't I just pull the expectation through basically the cost function anyway, whether it's homogeneous or not? And then, I mean, you'd get a more complicated thing, but wouldn't it just be like a sum of probabilities, which also seems okay to me?
Yes, but in this case it's easy because like there are only two players. But if you have a full network with many different things, the probabilities you need to add in any given arc is going to depend on the whole topology, depending on what path end up being chosen by every player. So yeah, you can always like expand the expectations, but then you cannot define it in advance. It's going to depend on the topology, what PIs are added into what arc. So it's going to be possible, but messy. And I want to have a closed form way to compute the price of anarchy. But yeah, we can talk more about that. So if you have ideas about how we can do this, that's fantastic. I want also simple parameterization of the price of anarchy on a single parameter, in this case being P, and see what happens there. Where P here is the maximum of the PIs. Maybe there is another world in which we can look at the average of all the PIs or some other way and still give some nice parameterization of the price of anarchy. So those are interesting discussions that we can go into in the Q&A part of the talk.
Okay, I guess yeah, but here you still have to deal with network topology to some extent, right? Because it feeds into X.
Yeah, totally, but exactly. But I'm encoding the whole thing through X, which is how many people chose that arc, and not a complicated sum of all different PIs depending on the identity of the players. So a congestion game is one in which depends not on the identity of the players, but just on how many players take that resource. So in that way, this can still be a congestion game in the basic definition of congestion game. If it depends on the identity, then it's not a congestion game anymore. It's just a final game that we need to analyze next door.
Thanks.
Yep, totally. I'm happy to continue the discussion there because I also want to generalize this as much as possible. So, so this lemma only says that I can write a condition that basically says when the game is going to be lambda mu smooth. And if you notice that inequality has many terms, basically what I want to focus on is that like the whole inequality is based on lambda mu, which is a number I need to set. I'm going to be optimizing for lambda mu, so that's going to be my decision variable. Then we have P. P is a parameter which is fixed in advance, which is going to be the one that is going to give us the parameterization of the price of anarchy. And then we have M and K, which are going to be just variables or names, which are going to stand for the different loads at the different equilibria or social optima that we want to explore for the different solutions when we want to compare one solution to another. So again, I say this again, the important things here is lambda mu are my decision variables that I want to optimize for, and the rest are just parameters that I want to use for my advantage. So let me show you that if we start from this Bernoulli congestion game, and I have that lemma that then I wanna use to my advantage, then the game is lambda smooth. So lambda mu smooth. So if I start from the cost function here, basically what we need to prove is the following inequality, and I'm just expanding. So CI of comparing these two strategies, the S prime and S, when one is the equilibrium, the other is the social optimum, which is what we're supposed to show that when we want to show that the game is lambda mu smooth. I can expand on this. I'm going to do this for a very simple case of the cost function x equal to x. This is done in the paper in the serious way with any cost function, etc. But let me do this here for the talk in an easy way. So if you expand, basically the way you expand, let me display a few things here. The way you expand is that you evaluate the cost function here on basically on the load on an arc, and the load of an arc is that me being there plus the number of players that are there and the strategy S minus I, which is all the rest, times P, which is the probability that people participate in the game. And the trick I'm going to do here is I'm going to replace the S minus I by S, which can have like more players, never is going to have less players or fewer players. And by doing that, I managed basically to write this as a cost function that is really close to the global cost function in which I'm mixing S prime and S. And the reason I want to do that is that then you can apply the inequality I showed you earlier in the previous slide in the lemma. And if you compare the two side by side, you'll see how NE of S prime and NE of S play the role of the K and P, sorry, the K and M that I have in this slide. And you can put them side by side, you'll see everything coincides. And when you do that, then basically what you do a little more algebra, and what you end up proving, if you assume that inequality is right in the lemma, then that the inequality you have for lambda mu smoothness is indeed valid. Anyway, it was a long way of saying, if you assume that this inequality holds, then immediately you have that the game is lambda smooth, and therefore the price of anarchy is what I had in the previous slide, which is lambda over 1 minus mu. So why do we do all this? I mean, I said lambda mu smoothness is the starting point of this. The reason is now we can optimize. So we know that if you can move the lambda mu's, we can find the best possible upper bound for the price of hierarchy. So I'm going to be minimizing the upper bound to get the best possible price of hierarchy. And now the constraints are that this inequality I showed you in the lemma needs to hold. And this inequality holds when for any arbitrary k and m, the whole inequality holds for a given p. So what we managed to do is, if you give me a p, which is your maximum participation probability, we converted this price of hierarchy estimation problem into this nonlinear optimization problem with infinitely many constraints. One constraint for every pair of k and m. And if you manage to solve that for any p, we can get the bound for the price of hierarchy as a parameter of p, which is what I wanted. And so that's what we do in the paper. So I guess all this was the introduction. The whole action that happens in the paper is to solve this problem. So I repeat that, making sure that like the idea comes across. If you give me any p between 0 and 1, which is the participation probability, what I want to do is I want to find the lambda mu that minimizes the price of hierarchy upper bound in a way that for any k and m, which are these parameters, it's still true that this inequality holds. Now, when you solve this for any p, or for all p's, which is what I want to do, what you'll see that is that in the optimal solution, the binding constraints in this nonlinear program are different. And that leads to different regimes that will lead to the optimal solution for the price of hierarchy, or for the actual price of hierarchy. So for some ranges in P, there are two tight constraints that will define the optimal solution. And for other regions of P, there is no two tight constraints. You'll get that, you know, the optimal point here is in the limit. As you take the limit, and the constraints are going to be changing as you get closer to the limit. So the limit only holds asymptotically here for some ranges of P. And I'll show you how that translates into the actual curve that defines the price of hierarchy.
But this problem only gives an upper bound on the price of hierarchy.
Yes, correct. You're totally right. Then we find matching lower bounds. So you're totally right. Exactly.
Okay.
Yeah, totally. And
so just following up on that line of inquiry. So you're saying even though what you've shown us so far would just be getting an upper bound, you actually do show that in this problem, this upper bound is tight, basically provide lower bounds as well.
That is correct. That's exactly the case. Yes, indeed. So we found a matching lower bound that has a given network topology and has so many players with the same probability we want. And we show that the price of hierarchy for that example matches exactly what we get from this mathematical program or nonlinear problem that gives us the upper bound. I'll show you the instances, although I won't go into details about like the calculations, but you'll see how they look like in the next slide. So the optimal solution has three regions or three phases. What's very interesting, and this is something we didn't anticipate, is that on the lower region, so for very small p's, and remember, I want to look at this when p was small just to see whether in this bound we'll get into the non-atomic bound of the price of hierarchy. We indeed go there because when p goes to 0, the price of hierarchy goes to 4/3 as anticipated, so that's nice. But not only that, it's also constant for p's between 0 and 1/4. So it's equally 4/3 for that range, and then it starts increasing between what I call P0 bar and P1 bar. So in that range it increases, and then it increases a little more, and it goes to 5/2 when P goes to 1. And let me show a picture, which is nicer than the equations in the previous page. So the way this looks like is what you see on the right. On the right, you can see the three regimes, which are the three curves that are displayed in blue, yellow, and green. The maximum of those, the upper envelope of those, is actually the price of hierarchy. Remember, I need to look at like the solutions with all the constraints are binding, so that's why I end up looking at the upper envelope of this. Notice that this is not convex nor concave, because like the first part is constant, the second part is concave, and the third part is convex. which is very strange, and it's not something we anticipate in any way. I do not have a very good intuition of why we have this change of convexity to concavity, or what these breakpoints mean exactly, more than knowing that they materialize because of the changing structure about the binding constraints in that nonlinear program I showed you earlier. But this satisfies some of the properties we expected. In the boundaries of 1 and 0, they go to where we expected them to go. And then if you look at the price of stability, the blue curve that you see on the left is coming from that paper I showed you earlier by Clear and Schaffer. Well, we managed to extend that to in the lower region, which is a region they haven't studied because it wasn't part of their model. But the curve they already have, and the curve nicely extends to the case of p equal to 0 in a smooth way, or in continuous way, as you can see in the blue curve in the picture on the left. As you ask, those are some of the examples for the regime of large P. This is the example that we came up with. Although the proofs are for congestion games in general, the examples are already for network games. So it's nice that you can give a network game and you have still a matching bound that doesn't use like the more maybe complex topological structure of a congestion game, but with paths and networks is still fine. Not only that, it's also linear. You see, there is no affine terms in this game. Linear is enough to have matching lower bounds here. And it has a nice structure. So the structure are in which, like any OD pair, you can take a very convoluted path, or you can take, which is the blue one, or you can take the red path, which is more direct. And the way the path like mix with each other gives rise to the price of anarchy that we wanted. But then when P starts to get lower, this example stops working and we need different examples. So for smaller P's, we like a small simple P-GU ends up working okay to give a matching lower bound. And we can do all the math and everything works okay, and you see the bounds match. Let me conclude this part so I have 10 minutes to talk or a few minutes at least to talk about the conversion side. So I guess to finish this part, I haven't discussed the non-affine functions. I think that's interesting, but we have to deal with the higher moments of the binomials. It's not clear how to do that. Another question is what we discussed already about the profit versus non-profit type of optimum, and how to compare that and how that relates to what happens in practice by maybe services that provide GPS routing in actual platforms in real life. So I think those are interesting connections that one can play with going in that direction. And the other is another thing that was also mentioned earlier is participation may be correlated and it's not independent, and how that changes everything. And so that's another interesting direction for further study. Let me use a few minutes to talk about conversions, because I feel that this other paper is also really interesting and connects to a lot of prior work and opens up nice research directions. Okay, so wardrobe equilibrium is the same concept that we discussed so far, but in a continuous setting where every infinitesimal is a decision maker or a player, and everybody is taking the shortest path to go from origin to destination. And so there are two ways you can take the limit here. One way is when the weights of every player goes to 0 and the number of players go to infinity. This is the usual way in which people have looked at this convergence to many players, and it usually has been used as a justification for wardrobe in the past. So we have many cars, every car is very small compared to the population, so therefore it's okay to look at wardrobe. I think a different way to take the limit, which is one I really like, is when the weights continue to be 1, but this is the participation probabilities go to 0. And that's a different interpretation of the whole setting of the limit, and that gives rise to the different limit, and I want to comment on that. So when the weight go to 0, for example, that's an example in which you have an atomic game with a weight equal to 1/n. In the limit, what you get is that most players take the upper arc here, because you have basically that's the one that is less congested, so most people will tend to go there. And in the limit, you get to the wardrobe equilibrium of 1 on the top arc and 0 on the other arc. In that setting, we can refine some of the earlier theorems by Horry and Marcotte and all the unsplittable setting that I mentioned earlier in the talk, and look at the splittable setting that was analyzed by Horry and Marcotte. We can look at the unsplittable setting of the atomic games that we are discussing here. So when the number of players grow to infinity, the weight go down to 0, and the demand converges in the limit to the demand of the non-atomic game. What we can prove is the result for the vector that describes equilibria. So this is not the result for the price of anarchy, this is the result for the equilibrium itself. So what we can prove is that in this setting, we can prove that as you go to the limit, in this case, the stochastics are given by the mixed equilibria, if any, if you have any that arises. What you can prove is that in distribution, the random variables that describe equilibria go to the atom in which the whole realization happens in the Wadrop equilibrium. So that refines the result from the past that allows us to go from the atomic game with mixed equilibria into the Wadrop equilibria, and things converge to where they should in this setting. Second, and this is what I wanted to mention in the last few minutes, was the case of the increasing number of players and probability is going down to 0. So in this case, the limit is different. And in this case, what we described earlier in the paper about Bernoulli game applies. What you can do is you can take your original cost functions and replace them by the binomial cost functions I talked to you about before. This is what you see on the right of the page, in which I replace the original cost function by 1 plus the expectation of the binomial for the rest of the players. So that allows us to handle the whole thing as an atomic deterministic congestion game. And if you do that, then you can look at the limit of the Nash equilibria as the number of players go to infinity and the probabilities go to 0. And in this case, as opposed to the Wadrop game I showed you earlier, you see how the majority of the players select the lower arc. Because in expectation, otherwise there are too many players selecting the top arc. So most people prefer to not take the risk and take the constant cost here, as opposed to be faced with a possible congestion on the top arc if too many players end up being realized in the network. So when you take the limit of this, when the number of players go to infinity and the probabilities go to 0, then you get the setting of a Poisson, and you can model this as a Poisson realization in every single arc. And what that leads to then is to then look at the cost function for every arc to be the expectation of the cost of 1 plus, that's me plus the rest, where the rest is Poisson with rate x, where x is how many other people may show up in that arc. So the point here being, taking one additional assumption that let me not get into because it is not like too binding in the sense that like polynomials, exponentials, all the usual cost functions are going to be valid for this assumption. What you get between these modified cost functions and this technical assumption is that in the limit, when the number of players grow and the probabilities go down to 0 and the demand converges, is that the loads in every arc converge to a Poisson random variable in the limit. So the equilibrium is stochastic in the limit. So the realization of the equilibrium is going to be Poisson in the limit for every arc, and the expectation of that Poisson in every arc in the limit is going to be given by a Wadrop equilibrium of the modified game when you replace the cost functions by the modified cost functions I told you earlier. So let me backtrack and say this once more, because I realized that it has many twists. What I told you is the following. If you want to solve this Poisson game in the limit when p goes to 0, what you need to do is the following. You can replace the cost function by this modified cost function I'm showing you here in the slide, where the modified cost function is the expectation of the cost under a Poisson. Now that you have the modified cost function, and this is an expectation of a Poisson, so this is deterministic in terms of the expectation. This is still a Wadrop game, and it's completely deterministic. So you can solve that Wadrop game. It's a deterministic Wadrop game in the usual definition. The solution of that Wadrop game is going to give you the parameter of the Poisson which is going to be describing the equilibrium, which is stochastic in the limit when p goes to 0. So if I give you an example, so if you start from this game in which there were 2 arcs and the cost function was x and 1, what I do is I replace these cost functions in the original game by the Poisson cost functions, or these modified cost functions from the Poisson, which are given by that. I already took the expectations under the Poisson, etc. So that's what I get. Now I solve this wardrobe game. And as you know, like if you solve the wardrobe game with the modified cost functions on the right, what you get is that all the load takes the lower arc, because the upper arc has cost 1 plus x, so it doesn't make sense to take that arc. And that gives you the rate, which is telling you how people are going to behave at equilibrium. And as you can see, that coincides with what we said in the example I gave you originally, which is this one. This was the atomic congestion game with Bernoulli players. And we discussed here how, you know, in this one, most people tend to go down. And that's exactly what you see from, you know, this chain of thought that this theorem gives you. I know the last few minutes were really fast. I'm happy to explore a little more of that in the questions, but let me conclude right now then with the 2 papers I referred to. In terms of open questions, I go to the Poisson because of the way I took the limit when the probabilities go to 0 and then goes to infinity. Are there other ways to go to the limit? Possibly. I haven't explored them, but interesting to look at other limits and see what happens there. And finally, going back to profit, non-profit, what are other ways to look at the adaptive price of hierarchy in the setting when you go to infinity number of players, and then when people may have different information structures about what they know about the game. So those are interesting open questions to continue to explore. Let me stop here. We have a few minutes for questions, then we're going to conclude, and we'll stay here for more informal discussion. Thanks, everybody.
Thank you, Nico, for a wonderful talk. We have time for a few questions.
I have a question.
I went really fast, so I apologize for that.
So one of the related congestion game is in transportation is the traffic assignment with elastic demand.
Correct.
Where the demand depends on how much cost the passengers experience. So one way to solve that problem is that we connect the origin and destination with an imaginary link and assume that those people who decide not to travel will just go through that link, and we have an appropriate cost function for that. Is there something we could do similar in this case and arrive at the same result?
I don't think so. I think these two games can be combined into making something more interesting. I think the big difference between the elastic demand setting and this setting is that here we assume the probabilities are exogenous and not endogenous. In the elastic demand setting, like the emergence of people traveling or not traveling depends on the actual equilibrium of the game. You know, if people end up taking too long to travel, then maybe they'll stay home or they'll use some mode of transportation, which is not driving, because like it's too long to travel by car in this case. I think the two should be combined because like some people may decide not to travel because of the conditions in the game itself. And some people decide not to travel because some exogenous events like being sick or the weather or something else. And I think the two things should be combined into like exploring a richer type of setting than either elastic alone or stochastics alone.
Right.
I think it's a great direction for further studies.
Yeah, thank you.
If I may ask a question, so just to sort of understand in your like the first part of your talk, right? So so essentially there is a given P, which is like an say upper bound on everyone's probability of joining, and then you're trying to characterize the price of anarchy, but this is also like a price of anarchy over all possible n, the total number of potential drivers. Right?
Yeah, over all possible n and over all possible networks and
All
not fixed
possible
networks.
Yeah.
So I'm taking, I guess, as usual, you define the price of anarchy over all possible networks, over all possible realizations of cost, over all possible n's, and over all possible p's. The only restriction I'm taking is that all pi's need to be less than p, where I fix the p and I study that dependence. All the rest can be the worst case, whatever that ends up being for that particular set.
But if you look at the optimization problem that you have to compute the price of anarchy, And if you just restrict it, like those constraints that seem like for all integers, pairs of integers, right? And if you just restrict it to like all pairs of integers below n, do you get a price of anarchy for like where the number of players is bounded but random, like potential? Like
no, because maybe this is, I guess, is your question whether when you fix n, if you fix n in advance, can you do better in terms of this game?
Yeah, I mean, can you use the same optimization problem to get a price of anarchy for that case? Where I know like the maximum number of drivers in the city is, I don't know, 1 million or something, right? So there can't be more than that. So does that?
Yeah. I understand. I think we're not able to give any kind of improved bounds if you fix n. I forget. You have the difficulty that when if you fix n, you can transform some of the cost functions to try to to maybe reverse the bound you're giving on the n. And yeah, I forget what we tried exactly, but we were not able to, I guess, fix n and give anything improved here. I think you have the other limit. So n can be large, and therefore maybe all this is not too binding. But when n is very small, you may say, okay, if you give me only 2 players, what's the worst you can do with 2 players? Mm-hmm. And in that setting, then the number of examples you can provide with 2 players maybe is very small. And because it's very small, then maybe you could do something better. So the price of anarchy may not be too large in that case, because you cannot induce really bad coordination with 2 players. As opposed to the non-atomic games. In non-atomic games, we already know, well, we know with 2 arcs, for example, you already do something really bad. And we know for the atomic games, you only need a few players to have the 5/2. But then in the whole continuum, I don't know what's the minimum number of players you need to support a given price of anarchy. And in that sense, we haven't studied like all the dependencies between how many players, what's the P, and what are the worst possible examples we can think of to do that. But yeah, I can see oneself like trying to impose that bound and seeing what happens.
So in your you're saying that there are only 2 critical constraints for any P. That so as long as n is high enough that those 2 critical constraints are appearing, then you are fine. Then you can still do it, right?
The critical, you mean the ones in the nonlinear program I showed you earlier?
Yeah.
Yeah, exactly.
Okay.
Yeah.
So you also said about the so in the standard wardrobe game, the Pico Network example, right? So the 2 arc example was the network that gives you the worst price of anarchy, right?
This one, yeah.
Yeah. So does it still hold in this setting when you have randomness in the number of players participating in the game? This is still the worst case example, or
no? I show you this one. So it depends on the regime of what P is. So I told you for large P, that example doesn't support the highest price of anarchy. You need examples like that. We know for atomic and P equal to 1, so the deterministic atomic, we know that the worst case example can be given by a triangle where people choose like the long I guess between any edge in the triangle, you can take the direct arc or the long arc or the long path. Mm-hmm. That's enough to support the 5/2 example for equilibrium in the atomic game. So that's an example that works for P equal to 1. You can extend that like in this range of P's using the example I'm showing you here in the slide. But Pico doesn't work for this case. No, you need more than Pico.
I see. So there is a way to create a network, the worst case network for a given P, or?
Yeah, exactly. So this is an example for the large P case. For
large P, you can actually create this kind of network.
If you give me any large P, I can instantiate this example with that large P, and that's going to give me a matching lower bound to the upper bound I showed you earlier.
I see.
There is a paper by Jose Correa and co-authors also that tried to give some of these upper bounds using single OD networks, because here there are many ODs. The question is, can you do the same with a single OD and symmetric players? And he does that asymptotically by making the network larger and larger. So people have looked at these things about what's the simplest example you can give to support the price of anarchy, a matching lower bound for the price of anarchy. we're happy in this case that you could do this with network games, and you don't need to go all the way to congestion games, which are maybe more general, but harder to define and harder to visualize than network games.
Okay, I think we can end the official part of the talk. And thanks, Nico, once again.